So, thank you for calling me to the stage. So, first of all, I'd like to thank the organizers of this meeting for the invitation. I'm happy to be here today and share with you the topic of my talk, which is the mathematical modeling, the diffusion test, which is a standard test. So I will show you some antibacterial activity of copper-doped tin oxide nanoparticles. So here is my agenda for today. Very briefly, I will review with you the literature about in vitro data versus mathematical modeling. Then I will show you typical in vitro data you can find these days in the literature. And then I'll switch to the synthesis and characterization of the tin oxide nanoparticles. Then I will show you the in vitro experimental design. And finally, I will present to you the data and the mathematical modeling of the data, in particular the Hill model. And then I will come to my conclusions today. So let me emphasize a very important point about this presentation today. If you look at the literature about in vitro data and how much the published in vitro data are using mathematical modeling to understand the data. So if you do the search in Web of Science, and I did it recently, so you will find close to 1 million papers published and reporting in vitro data. However, only about 0.3% of this data includes some mathematical modeling. And so it seems there is a big challenge to move from a qualitative analysis to a quantitative analysis. And actually, to bridge this gap in terms of in vitro data and analysis of this data. And to bridge this gap, actually, you need two important points. First, the mathematical model itself. Second, a way to analyze the data using the mathematical model. So actually, these two pieces are around for over 100 years. So the mathematical model to analyze in vitro data, the first model was proposed actually more than 100 years ago, in 1910. It was proposed by Archibald Vivian Hill. So it's a British physiologist. And the second piece, so how you can take the data and use your mathematical model to analyze the data. So that was proposed almost over 200 years ago. So it's the curve fitting. So it was called the least square fitting. It was proposed actually in 1795. And it was proposed by the German mathematician Gauss, Carl Friedrich Gauss. So then, in conclusion, we have the two pieces to bridge this gap, taking from a qualitative analysis to a quantitative analysis. However, if you look more closely at literature, you can see that in the last, let's say, in the last 15 years, the number of papers that include a mathematical analysis, which means a mathematical model and some strategy to analyze the data. So in the last 15 years, actually, it duplicates the number of papers, including the mathematical modeling. So that makes some hope for the future, actually. Uh, then, however, most of the data you can find these days in the literature are presented like this slide. So I just took one paper from last year, but you can search very quickly. You will see most of the data published regarding the cell viability. They look like the data I'm showing in this slide. So this slide just shows the cell viability assay using two tumor cell lines, the T24 and the EJ cell line. So these two cell lines were uh, actually tested against a chemotherapeutic agent, which is ecnatin. And the typical data is the cell viability in the y-axis versus the concentration of the challenging molecule. Here, you can see the concentration in micromolar on the horizontal axis, and then the data are the symbols in both plots. And the assay were performed 24 hours, 48 hours, and 72 hours after the incubation of the cell line with the chemotherapeutic. And the solid lines are just, let's say, linking the experimental data, are just guide to the eye. And of course, there is no quantitative analysis, but sure, you can extract some information from this. Uh, but I would say obvious information as you increase the concentration of the challenging molecule. In both cases, the cell viability reduces systematically. And also, if you increase the time of incubation, like coming from 24 hours to 72 hours incubation, the cell viability reduces too. Beyond this, qualitative analysis is very difficult to make any prediction, any precise prediction you can extract from this data. So now let me show a little bit about the material we use to challenge two cell lines and show you how we performed the analysis of the data. So we synthesized actually tin oxide nanoparticles. And to make the synthesis, we use the well-established Piccinni's method. So in this method, actually, we mixture the reactants, in this case, tin chloride, and we use tin chloride doped with copper, and the copper was included as copper nitride. And this Piccinni's method actually it uses a organic molecule, in this case citric acid. It's very standard. And we perform the synthesis of tin oxide doped with copper, and the copper doping went up to 30 mole percent doping. So we just mixture this, make a pellets, and then we bring the pellets into the furnace, and we synthesize this in the typical temperature range from 700 to 1400 Celsius. And we can perform the synthesis a few times. In every cycle, you check the crystallinity of the material. If you find the crystallinity is not good enough, you can do the sintering again. So we perform this sintering using copper as a doping. So we might have copper-doped tin oxide nanoparticles, and the copper went from 0 up to 30 mole percent. So all this material, it was characterized using different techniques. Let me show you just a couple of them. So the morphological characterization we performed using transmission electron microscopy and also high resolution transmission electron microscopy. You can see on the panel on the left-hand side, this is the high resolution. You can see the distance, the typical plane distance inside the nanoparticles. In the middle panel, you can extract the particle size distribution. On the right-hand side, you can see the histogram, the particle size histogram, which are the vertical columns. And this was particularly the sample 2.5 mole percent copper. And we can curve fitting this data using a log normal distribution function. You can see down here, just below the particle size histogram, you can see the description of log normal distribution function. You can extract the mean size and the size dispersity. So in this particular sample, 2.5 mole percent copper, the mean diameter was about 8.3 nanometer. And dispersity below 0.3, which means it's a very good dispersion. So we perform, besides this, we perform different characterization, like, for instance, Raman scattering, optical Raman scattering, so to understand better the materials characterization. So regarding the structural characterization, I can show you the X-ray diffraction on the left-hand side, and all the data we performed the heat weld refinement, and this is the 30 mole percent copper doped sample. And on the right-hand side, I can show you the size of the nanoparticles in nanometer as a function of copper content. And you see that there is a systematic decrease in the mean size of the nanoparticles as the copper content increases from 0 up to 30%. A very important point here is over about 10% copper doping, actually a second phase emerges, and then you can see on the left-hand side. So the second phase that emerges is the copper oxide. So above 10% doping, besides the tin oxide nanoparticles, we have also copper oxide. But that is a minority phase, actually. So sample characterization was performed using different techniques. And now we use the standard, well-established in vitro disk diffusion experiment. Before we went to experiment actually using the cell lines, we performed some investigation of the diffusion phenomena itself. So here we have on the left-hand side, a culture medium, which is agar, inside the plate. And then we studied the diffusion of the copper ion, copper 2+ ion, inside the culture medium. So you see in the center is the copper doped tin oxide sample. And then we can look at the transparency of this culture medium, and that scales with the intensity of the copper, which is diffusing from the center. And you can see the plot. We have two near to, let's say, the 0 time. Actually, it's not the 0. It's actually 10 minutes. And then we can see the other plot, which is 48 hours. This is the picture of 48 hours. And then we can extract the intensity as a function of the distance from the center. And we found that the diffusion process, it fits very well with the Fick's law. This is the typical standard differential equation that describes the Fick's law. And the data, as you can see on the left-hand side, for instance, the solid red line is the best fitting of the data for the 48 hours diffusion. And actually, we could fit the data not using just one component of the diffusion, but actually two components in such a way that we have two diffusion coefficients, diffusion coefficient 1 and diffusion coefficient 2. And it's important to remind that diffusion coefficient goes with the Stokes-Einstein equation, which is diffusion coefficient scales with the inverse of the typical size of the object which is diffusing. So we found this data actually. So once we understand the diffusion process, we can step forward and perform our experiment using the standard disk diffusion experiment. So here I can show you, we tested actually two bacterial strains. So a gram-positive bacteria, which is S. aureus, and a gram-negative, which is Escherichia coli, E. coli. And then on the left-hand side, you can see the typical measurement of the diameter, actually the inhibition zone diameter. So inhibition zone diameter is DIZ, and the reference diameter is DR. Actually, the reference diameter is the diameter of the spot, which is a paper, immersed in the thin oxide nanoparticles. So thin oxide nanoparticles are deposited in the paper in the center. And here on the middle, you can see the standard diffusion test. On the A panel, we are testing the tin oxide, no doping. On the B, we are testing the 10% copper doped. You can see the inhibition, typical clear inhibition zone diameter, and the center is the reference diameter. And so the four pictures on the upper part are related to the S. aureus, and the four pictures on the lower part are related to the E. coli. So we measure the DIZ, which is the inhibition zone diameter, and then we argue that the cell viability scales with the inverse of this inhibition zone diameter. We can normalize this. We can use the reference diameter to normalize the data. So we can measure the cell viability as a function of the inhibition zone diameter. So then we can use the Hill model to make the fitting of the experimental data. So here is the Hill equation that scales the cell viability as a function of the dose. The dose is the D parameter. And so, and the cell viability scales with two normalizing constants, V0 and V1. Besides this, the cell viability depends on the dose, which is the concentration of the challenging material. But there is a very important exponent, which is the Hill coefficient, E, here. So this is the standard Hill model. From this model, you can extract important information such as the lethal dose 50, LD 50, which relates the concentration of the challenge molecule to reduce the cell viability by half, 50%. Or you can extract the benchmark dose, BMD, which is the concentration of the challenging material, to reduce the cell viability by 10%, or any other value you may wish. So the important parameter here is the Hill coefficient. And the Hill coefficient is a very interesting parameter. There's a border, which is number 1. So you have Hill coefficient below 1 or Hill coefficient above 1. What is the difference? When the Hill coefficient is below 1, it means the first molecule that binds the cell membrane just reduce the probability for the next molecule to bind to the cell membrane. However, if the Hill coefficient is higher than 1, that means the first molecule that binds the cell membrane just facilitates the binding of the next one. So this border, the Hill coefficient equals to 1, is very important. We can extract all this data just performing the analysis of the experimental cell viability using the Hill model, and of course a mathematical computational approach to extract and fit the data, which is the least square fitting. So here are the data. On the upper part, we see the S. aureus test. The green symbols are the experimental data, so you can see that the cell viability reduces as the copper content, which is the doping copper in tin oxide, increases from 0 to up to 30%. In the lower part, the red symbols is the test by E. coli. You can see the tests are quite different, the results. So the tin oxide doped with copper has a higher efficacy for S. aureus than it has for the E. coli. The black solid lines you can see in both plots represents the best curve fitting of the data. I can emphasize on the right-hand side that the the Hill coefficient for the S. aureus is 6.7, and for the E. coli is about half, 2.9. So it means in both cases, the first material that binds to the cell membrane just facilitates the next one. But of course, for S. aureus, this facilitation is higher than for the E. coli, and that leads to important results. So the LD50 for S. aureus is about 1/3 of the LD extracted from the E. coli. Likewise, you can see the BMD for S. aureus about half the value for BMD from the E. coli. So if you don't have a curve fitting process, for sure, you will never get some idea about the Hill coefficient, which brings in a very, very important information about the cell response in both cases. Of course, the LD50, looking at the data, you roughly, you can find, estimate, let's say, the LD50. And estimation of the BMD is a little bit harder than the LD50. But you can look at and guess some data. However, if you perform a curve fitting, you can extract this important information, including the precision of the data. So let me draw a few conclusions about this presentation today. And so quantitative analysis provides extraction of the Hill coefficient and against qualitative analysis. So no way to extract the Hill coefficient, only performing some qualitative analysis. Besides this, quantitative analysis provides extraction of BMD precisely, and qualitative analysis just gives you an idea. And likewise, quantitative analysis provides extraction of LD50, and qualitative analysis just gives you a guess. And finally, if you perform a quantitative analysis, it allows you to distinguish the cell line bioresponse precisely. And qualitative analysis does not, provides you a precise bioresponse. So I would like, again, thanks to the organizers of this meeting and for the invitation to be here today. Was honored to be here and share with you this talk today. And also, I would like to thanks all of you online attending my talk. Thanks. And if you have any question, I'll be happy to take the question. On the lower part of my slide, you can see my email address. So it's very simple. Perhaps you can picture. And if you want to be in contact with me, please feel free to make the contact. So back to Mrs. Chair. Thank you.